What if I told you there's this hidden arena, right? An invisible stage where all the bizarre, mind-bending rules of quantum mechanics actually play out? And look, this isn't some sci-fi movie concept. It's the real mathematical world that makes quantum computing possible. So today, we're going to pull back the curtain and explore that stage, the Hilbert space.
All right, so here's how we're going to tackle this. First, we'll go from the bits we all know to these powerful new things called qubits. Then, we'll actually step into the quantum arena and get the lay of the land. After that, we'll learn the rules of the game. And this is where it gets fun. We'll see how adding more qubits gives us this insane amount of power. And finally, we'll tie it all together to see why this abstract idea is a total game changer.
So first question, why do we even need a whole new mathematical playground? Well, it's because the players in this quantum game, the qubits, they're just built different. They're nothing like what we're used to in our normal classical world. Just look at this comparison. Over on the left, you've got your standard classical bit. Think of it like a light switch. It's either on or it's off, a 1 or a 0. Simple. But then you look to the right, and you've got the qubit. The qubit is way more like a dimmer dial. It's not just stuck at on or off. It can exist in this weird mix, a superposition of both 0 and 1 at the exact same time. Its state isn't one definite thing, but this whole cloud of possibilities. Right? That's the big question. This bizarre property, this superposition thing, it just doesn't fit into our everyday logic. And to handle something that can be in multiple states at once, you need a very special kind of space. One that's big enough to hold all of those possibilities simultaneously. And that, right there, brings us to the main event. Welcome to Hilbert space. This is the mathematical stage where, believe it or not, all of quantum mechanics unfolds. Okay, I know. That definition is a total mouthful. Let's just forget the jargon for a second. Here's the core idea. Think of a Hilbert space as the perfect map for a quantum state. You know how a simple number line can show you where a bit is? It's either at the point 0 or the point 1. Well, a Hilbert space is like this huge, multi-dimensional map that can pinpoint a qubit state anywhere within its entire ocean of possibilities. And this image, the block sphere, shows it perfectly. A classical bit, it could only ever be at 2 spots, the very top, the north pole, representing state 0, or the very bottom, the south pole, for state 1. That's it. But a qubit can be at any single point on the entire surface of this sphere. And every single one of those points represents a unique combination, a different superposition of 0 and 1. All right, so we've got our players, the qubits, and we've got our arena, the Hilbert space. So now let's get into the really interesting part, the rules of the game. How do these things actually behave? This quote really nails it. Being in multiple states at once isn't just some weird quantum quirk. It's the secret sauce. It's what lets a quantum computer check out tons of different paths all at the same time. We're talking about a level of parallel processing that classical computers can literally only dream of. Now, mathematically, we write down this superposition using this simple but incredibly powerful equation. All it's saying is that the qubit state is some weighted mix of state 0 and state 1. And those weights, represented by those 2 little Greek letters, alpha and beta, they are absolutely key. So what are alpha and beta? You can think of them as probability dials. They control the chances that when we finally measure or look at the qubit, it snaps into being a definite 0 or a definite 1. And that last rule there just makes sure that the probabilities always add up to 100%. I mean, it makes sense, right? When you look, it has to be one or the other. Okay, so a single qubit is pretty cool. But the really crucial part, the thing that gets everyone so excited, is what happens when we start putting more qubits into the system. This is where things get wild. Now here's where the real magic happens. When you bring 2 qubits together, you don't just get 2 separate spaces sitting next to each other. No way. Imagine you have 2 maps. You don't just tape them together. You create a brand new, bigger map that shows every possible combination of locations from both original maps. In quantum mechanics, we call this a tensor product, and it literally multiplies the possibilities, creating this shared arena that is exponentially larger. So let's build this up. We start with 1 qubit. It can be in a superposition of 2 basic states, 0 and 1. Simple enough. Now, let's add just 1 more qubit. Because of that multiplying effect we just talked about, the system can now explore 4 distinct states at once, 0, 0, 0, 1, 1, 0, and 1, 1. Think about that. We added 1 qubit and we doubled our computational space.
And this is the incredible payoff. For any number of qubits, let's just call it n, the system can explore 2 to the power of n states, all at the same time. This isn't just adding one at a time, this is explosive exponential growth. This right here is the heart of the quantum advantage.
So let's zoom out. Let's connect all this abstract math stuff back to the real world and see why having this gigantic computational space could literally change everything. Because quantum computers can explore this enormous Hilbert space and juggle countless possibilities at once, they can take on problems that are just completely out of reach for today's computers. We're talking about things like designing perfect, life-saving drugs by simulating molecules exactly, or creating unbreakable codes and, breaking the ones we use today, or building AIs that could solve problems that would take a normal computer longer than the entire age of the universe. And here is the thing that will absolutely bake your noodle. Nobody knows why. Nobody knows why the universe works this way. There's no deep-down reason we found for these quantum rules. We just know, from experiment after experiment, that this weird mathematical world of Hilbert spaces is a perfect description of reality at the tiniest scales. It just works. So, as we're finally starting to build machines that can actually navigate this quantum arena, the real question is the one you see right here. This vast, unexplored territory of these exponentially growing Hilbert spaces. It isn't just math on a chalkboard. It's the map to the next great frontier of human discovery. What are we going to find there?